Okay, hi everyone. Welcome to today's presentation regarding parallel programming principle. Okay, in this lecture, I will explain about the share memory implementation, and then regarding the concept of parallel programming. Yeah. Okay. All right. Today topics organized to altogether 10 part or 10 items. First, introduction. Second, regarding basic design. And also next we'll cover performance analysis, performance loss, and common sources of performance degradation. And then examine fundamental parallel structure and optimization technique. Lastly, we will apply all these principle to detail the case study before finally we draw our conclusion. Okay, first and the foremost, uh, why parallel? Yeah, why parallel? To understand uh, why we must write parallel code, we have to look at modern hardware constraint. Yeah, in the more loss. Yeah, so we got more loss, which historical guarantee a steady increase in a single core clock speed. So has significantly slowed down. Okay, it shows that in a single core clock speed. Okay, instead of the faster individual core, modern chip manufacturer deliver multi-core processor featuring anywhere from 8 to 128 cores, for example, in a single core, single core on a single socket. Single socket means one connection to the server, and then your machine itself, Some machine may be at core, 4 core, depends. Okay, all right. So to meet the intensive processing demand of AI and also big data analytics right now. There's an emerging trend right now. Developer must write a software, that spread workloads across all these cores, the cores, Furthermore, running multiple core at lower frequency deliver much better energy efficiency than pushing a single core until its physical limits. Okay, so that's why we need to have this kind of the parallel computing. All right. Okay. To measure how well your code or software scales, we actually rely on three metrics. Okay, three metrics. We got a speed up, efficiency, and also scalability. So for the speed up, actually, this is the calculation. Okay, so which evaluate our performance gains by dividing a total serial of execution time by parallel execution time. Okay, that's to calculate the speed up. Okay, and then for the efficiency, which measure how effectively we utilize our hardware by providing overall speed up. Sorry. So for the efficiency, we utilize our hardware by dividing our overall speed up by the processor count, which is P. Okay, so this is how we calculate the efficiency. And for the scalability, which we analyze through two points here, whether strong or weak. Strong scaling looks at how our execution time decreases when keeping the problem size fixed while adding more processors. Okay. Weak scaling looks at whether we can maintain a constant execution time by increasing our problem size proportionally as we add more processor. So that's mean scalability in terms of strong and also weak. All right. Okay. So this is the key metric that normally we evaluate our algorithm, software, and so on. Yeah, and this is very important point that we need to know that. Yeah. All right. So programming models. When building a parallel system, yeah, your choices of programming model is depends by your hardware architecture actually. Yeah. First, we have to share. We have the share memory here. Yeah, we got share memory, which is we use OpenMP, and for the second one is distributed, which is MPI. Yeah. Okay. So in share memory, yeah, in this model, all threads operate in a single, yeah, in a single unified address space because memory is a share. All right, and then communication between thread happen implicitly when they read or write to the same variable. This is the thread-based paradigm that is highly ideal for the multi-core processor within a single system node. Okay, this one. Okay, all right. And then for the second one, we have the distributed memory model, typically implemented through the MPI or message passing interface, okay, or MPI. Here, separate processes run in completely isolated address space. Yeah, isolated address space because one process cannot see another data. All communication must be explicitly, meaning data must be which is packed and sent over a network uh, in a fabric. Yeah. Okay. This process actually based on the ideal for the multi-node computing cluster. Okay. This is how it's work actually. Yeah. Okay. So for the MPI. And then for the modern high performance PC right now, we leverage they call a hybrid model. So we combine currently, okay, combine between this OpenMP and also MPI. Okay, this Apple combine both world by running thread-based OpenMP within a single compute node to handle local processing, and for the process-based MPI between individual nodes to manage network communication across the cluster. Okay, that's why we need this kind of the model which is combined. Okay, later we will have this kind of the activity which is we combine with OpenMP and also MPI, yeah, for the high performance computing. Okay, next. Okay, performance metrics. This is the metric that we already knows that at the beginning. I mentioned that. Okay. Okay, let's formulate the exact mathematical equation we use to audit our performance, software performance. Yeah. First formula is a speed up formula that you can see here. is a sequential execution time, which is T, yeah, T, and then divided by parallel execution time, which is T parallel. So this both is T. So this is how we calculate the speed up. Okay. And then next we calculate the efficiency by dividing our calculated speed up by our processor count. Okay, this P, processor count. We divided in order to get the efficiency, which mathematically expand to sequential time divided by the total number of the processor. Correct? Okay, so which mathematically expand to sequential time divided by the total number of processor times the parallel execution time. This. Okay. So this one for efficiency. Another word, we divided that. Okay. So this is mean. Okay. For the P. All right. So when we track a scalability, okay. So of course, in scalability, there are 2 points, yeah, whether strong or weak. If we use a strong means, big problem, we not increase the problem size, which is the array, we fix that, but we increase the number of processors. That's a strong scalability. For the weak, okay, we increase the problem size with the processor. So there's a weak scalability. Okay, this is mean by these two. Okay, all right, please take note about that. Yeah. Okay, performance law. To understand the upper bound of strong scaling, yeah, when we say that strong scaling, we look at the Amdahl law. Okay, here. Sorry. The formula is stated as you can see here, yeah? All right. So in this equation, F represent the strictly sequential fraction of our code. What is that? The sequential fraction, this F. So, while P, where's the P? P is our total number of processor. Because the serial fraction F cannot be parallelized. Okay, this one, the F cannot be parallelized. So F, because of that, in place a strict upper limit on our maximum possible speed up, regardless of how many hundreds of processor we add to a fixed size problem. Okay, so let's step through a concrete example. Okay, suppose we have a program where 60% parallel code on on 8 processor, which means our non-parallel sequential fraction is F sequential is about is a 40%. Yeah. Okay, for the sequential, all right, 40% or 0.5, for example. Yeah, in this case. So if we want to, okay, this one, if we attempt to accelerate this fixed problem across 8 processor, so our speed up calculation become 1, okay, divided by 0.4 plus 0.6 divided by 8. All right. This evaluate to roughly 2.1. Okay, roughly 2.1. Even though we deploy 8 processor. Okay, so here is the 8 processor. Our actual performance gain is heavily limited to 2.1 of the speed up because of 40% of the serial bottleneck dominates the execution runtime. Okay, so that's the reason. even we increase the number of processor, but the speed up still, okay, roughly, if you can check that and then you can try, calculate that. So we'll get almost only double, okay, from what you can see here. Okay, not much because of this serial bottlenecks. Yeah, they call serial bottlenecks. Okay, so this become a dominance to this because of that. Okay, because 60%, because of this 40% of the serial fraction. All right, okay. So while Amdahl law just now, yeah, focus on fixed problem size, yeah, fixed problem. Okay, Gustafson basis law shift. This one Gustafson, yeah, Gustafson shift the perspective to scale, speed up. All right. So this law recognizes that when we scale up our hardware, we naturally use that power to run larger, more complex data set. Then the mathematical formula for this scale speed up, as you can see on the screen right now, this one. Okay. So in this case, yeah, S represent the serial fraction. Okay, in this case, S represent the serial fraction of our application. This model explicitly accounts for problem scaling because our parallel workloads expand to fill the larger processor grid. The relative time spent on the static sequential fraction shrink because of that. Okay, let's look at an example. Imagine we have an application with 10% serial fraction. This one, yeah. So 10% serial fraction meaning S is 0.1, yeah, correct? 0.1, if you can see here, 0.1. Okay, so if we scale our problem size up across 16 processes, so our maximum scale speed up is calculated as 16 plus 1 minus 16 times 0.1. So what happened? This evaluates to an impressive speed up. Impressive speed up. This one. Okay. Impressive speed up bound of 14.5 out of maximum possible, which is 16. Yeah. This proves that when weak scaling is applied to expanding data set, we can achieve highly efficient utilization of massive hardware setup. All right. Okay, now looks another advanced performance metrics. So curve flat metric, yeah. So when analyzing a real world performance data, yeah, standard speed up equation can mask, yeah, hidden design flaws. To export these flaws, we look to advanced metric like curve flat metrics. Okay, the formula to calculate this, as you can see here. So this is the formula from the curve flat matrix. Okay, this metric actually tracks the experimentally determined, determined serial fraction, denoted as a E, So E is a serial, okay, which directly capture parallel overhead, okay, E, So means measure the parallel overhead, which is E. By tracking how the value of E shift as you scale up processor count, right? So you can pinpoint exactly why your application is losing performance. First, if you increase your processor count and the calculated value of E remain relatively constant. You can check that, yeah? It means your algorithm is simply has a fixed, unparallelizable sequential block that is limiting your speed up. However, if the value of the value, however, if the value of E increases alongside your processor count, it serves as a clear warning sign of growing parallel overhead, such as network communication delay or severe synchronization barrier. All right. Okay. The next one, advanced performance metrics for the ISO efficiency metrics. So another critical advanced diagnostic tool is the ISO efficiency metrics, which is used to explicitly measure system scalability. Okay, instead of measuring time or speed up directly, ISO efficiency determines the exact rate at which your overall problem size must grow relatively to your processor count in order to maintain a completely constant level of parallel efficiency. If an application processes perfect scalability, it exhibits a linear ISO efficiency relation, meaning if you double your processor, you only need to double your problem size to maintain peak hardware utilization. If your problem size has to grow exponentially to maintain efficiency, your algorithm is fundamentally unscalable over large hardware configuration. Okay, that's a conclusion they made. Okay, we can use this metric also to look for the scalability. All right. So now common performance, common performance bottleneck. So this categorize list of the performance losses like load imbalance, communication overhead, synchronization, and also memory hierarchy. To design highly optimized system, you must learn to identify and mitigate the four primary sources of performance loss. One, load imbalance. Okay, the first one, load imbalance. This occurs when a workload is distributed unevenly, across your hardware, leaving a fast processor sitting completely idle while waiting for the slowest thread to finish its work. So the solution require an implementing, better domain decomposition strategy to balance the computational weight evenly. All right. So that's for load imbalance. For the communication overhead, this bottleneck stems from latency and bandwidth limitation when data travel across a network. So the solution is to restructure your software so that you overlap active computation with background communication phases. And for the next one, which is synchronization. Overusing synchronization mechanism like barrier, locks, or critical section forces your multi-core processor to stop running. So it can happen, stop running in parallel and execute sequentially somehow. So the fix is to minimize synchronization point across your execution loops. Okay, this also very important things. So memory hierarchy. These loss happen when poor cache usage leads to constant cache misses or file sharing, forcing the CPU to stall. To stall while pulling data from slow main memory. So the solution requires optimizing data locality to keep calculation tightly aligned with the hardware cache line. Yeah, all right. Next, common parallel pattern. Okay, rather than designing parallel application from scratch, we rely on established parallel pattern to structure our workload. Embarrassingly parallel, this pattern constantly of entirely independent tasks that require absolutely no communication or synchronization between threads. It is highly ideal for distributed computing frameworks. And next, divide and conquer. This pattern recursively divides a complex problem into smaller subproblem, yeah, and then computes them concurrently and then combine their result. Classic example include merge sort, FFT, or fast Fourier transform. Okay. And next, regarding pipeline. So this pattern flow that linearly through a continuous change of distinct specialized stages, which like an assembly line. This is the standard choice for video in media stream processing. Okay, this is good for, this kind of the application, okay, pipeline. And next, map reduce. So this data parallel pattern partition, yeah, massive data set into parallel block that we did, yeah. We do actually, yeah. There's a purpose. So processes, okay. So this data actually, data parallel pattern partition massive data set into parallel block. Okay, processes them independently in the map phase, for example, and aggregates them into a structured result during a reduced phase when we run that, yeah, reduced phase. So it forms the foundation of a modern big data analytics. So this is right now the trending. We are using that, yeah? Okay. Next, OpenMP optimization. Okay, when optimizing shared memory system, yeah, running OpenMP, you must focus on thread behavior and hardware cache utilization. First, you want to eliminate file sharing by introducing memory padding so that threads are not modifying different variable on the exact same cache line. Yeah. Second, you must select optimal chunk size within your loop scheduling clauses to keep workload uniform. Yeah. Third, you must actively reduce critical section to keep threads from stalling. Hang. Yeah. Fourth, use the no wait clause or function no wait. Yeah. Where possible means whenever it is safe to do so, which remove implicit barrier at the end of parallel loops. Finally, implement strict thread affinity, yeah, control to pin specific thread to physical core and utilize task-based parallelism to handle irregular, non-uniform workloads efficiently. Okay, so this is kind of the OpenMP optimization. And then for the MPI optimization, when optimizing for distributed memory system like using MPI, the primary objective is to manage network traffic efficiently. First, uh, first is non-blocking communication routines such as MPI I send, MPI I receive. This allow a processor to initiate a network data transfer and immediately return to computing, hiding network latency. So second, use a message aggregation to bundle multiple small variable into a single large network transmission to reduce latency penalties. Third, design MPI derived data type to package and send complex, non-contiguous data structure efficiently. Fourth, always structure your software to overlap active computation with background communication loop. Finally, utilize topology and decomposition to ensure your logical communication grid maps directly to the physical layout of your server cluster. That's very important. Okay. All right. Next, we go for the case study of the OpenMP, MPI, and also hybrid approaches, especially for the metric multiplication. Okay, let's examine how we apply this abstract optimization technique to our first major case study, metric multiplication. Multiplication. Our strategy is entirely depend on our targeted model. In OpenMP implementation, we focus on loop optimization. We use structural loop tiling to feed data perfectly into logical cache line and deploy nested parallelism to fully saturate multi-core CPU. All right. And then in OpenMP, OpenMP, for the MPI, we focus on spatial distribution. We split the large metric into distinct blocks using 2D blocks decomposition. And after that, execute advanced communication pattern like Canon algorithm. And the next one, in a hybrid environment, we combine both methods. We use MPI to distribute macro blocks of the, this one, OpenMP. So we use MPI to distribute, that's first thing, to distribute macro blocks of the metric between different servers across the network. And then use OpenMP within each server to compute the sub-matrices concurrently across local CPU core. All right? Or nodes, same thing. Some we say node, some we refer to core. All right. Okay, look the first case study, which is regarding N-body simulation. Okay, our second case study here. Okay, for example, N-body simulation, which track the physical motion of a system of particle interacting under mutual forces. This problem presents unique parallelization challenges. Okay, under OpenMP, we manage a spatial. First of all, under OpenMP, we manage spatial structure locally. We implement a spatial decomposition technique such as Barnes-Hart octree algorithm in order to reduce computational complexity. Yeah. And then for the MPI, we manage a spatial distribution globally. We implement physical domain decomposition. I mean, carving space into region and utilizing a ghost cell communication pattern to exchange boundary data between nodes or core. Yeah. All right. And then next one is from a performance standpoint. The core challenges in an n-body simulation actually revolve around managing complex communication pattern and overcome severe load balancing hurdles as particles naturally cluster together into dense partial hotspot over time. Okay, that's the challenges in this n-body simulation. Okay, the detailed case study, the next detailed case study of n-body simulation. Okay, so you can see the cosmic web particle cube visualization alongside with the problem. I will explain that. Okay, okay, this is a particle movement in the 3D space. They move around. Okay, okay. Looking closer at the n-body problem. Yeah. Our core definition requires us to simulate an individual portion of n particle under mutual physical forces. Okay. If we implement this using a direct or naive method where every single particle calculate its physical pulse against every other particle. So the algorithm hits a massive 0 and power of 2 computational complexity. Okay, that's a common. We use this kind. Okay, this simulation style is standard across astrophysics and then cosmic structure modeling and molecular dynamic. Okay, so we use and then also common in this kind of field. Okay, even my PhD also we get the data from this particle movement. All right. So simulate the scenario, okay, based on the movement of particle. So this kind of the things. Okay, all right. Okay, to paralyze this effectively at scale, yeah. So we need to have this kind of the we want to repeat because this is not the single data that you can see only the single image, but we have tried to imagine that it's not the single data set, it's a huge data set. That's why we need to parallelize all the movement. Otherwise, it takes years to running all this simulation. Okay, that's why we have the parallel code to make it easy our life, especially in the current imaging trend right now. Okay, all right. To parallelize this effectively at scale, we select targeted approaches. All right. OpenMP utilize partial decomposition. Okay, partial decomposition with octrees under the Barnes-Hart optimization to simplify local tracking. And then MPI split. And then MPI this split the spatial space into domain and manage data transfer through a ghost cell structure. All right. And our hybrid approach, combine both to execute massive or multi-million particle simulation across a large cluster architecture. Okay, try to imagine that. Okay. And next, Cannon, Cannon algorithm for metric multiplication. Okay, so in the diagram, you can see the diagram shows a metric block shifting over discrete time step for C equal A times B. All right. So let's step through the explicit execution behavior of Cannon algorithm for metric multiplication. Yeah. The key idea behind Cannon algorithm that it allows a block-based metric multiplication while minimizing overall network communication overhead. It achieves this by shifting block of our matrices across a 2D toroidal processor grid. Yeah, as shown in the diagram, we have 9 blocks mapped. Okay, how many altogether? 9 block map to a 9 concurrent processors. So that the algorithm move data in 3 explicit steps. First, initial skewing. Yeah, initial skewing. So where metric A blocks are shifted circularly to the left based on their row index. And metric B blocks are shifted upward based on their column index to align initial sub-matrices. Okay, that's the first step. For the second step, shift and multiply iteration. So means that each process, the second one. So each process multiply its currently held local blocks of A and B, then accumulates that partially result directly into its block matrix C. Then then perform a stepwise circular shift, means that moving blocks of A to the left and moving block of A, if you can see here, block A to the left and block of B upward. Okay, this is how it is. And then next, accumulate partial result. So this shift and multiply loop continues for a number of iterations equal to the grid dimension until the total of submatrix C is fully compiled as shown by the example, the sample of equation of block C. Yeah, this. All this related to this diagram. Yeah. Okay. So next is the pseudocode. Yeah, pseudocode for Cannon loop utilizing using MPI, send, receive, replace, and so on. Yeah. So here is the concrete MPI pseudocode for implementing Cannon algorithm. Okay. So the primary execution loop run from 0 up to the grid size. There's a grid size there, yeah. Okay. And then on line 4, line 4, we perform a completely localized submetric multiplication through multiply blocks. Okay, line 4. Updating our local C, buffer. Immediately following the calculation on line 7 and also 8, we issue an optimized network call, MPI, send, receive, replace. Okay, yeah. This one. Okay, this routine perform a simultaneous data send and receive operation, replacing the content of local metric buffers in place. So it automatically shift our local A, block to our left neighbor, and our local B block to our top neighbor. All right. Okay. So to implement this, clearly we use MPI chart create chart create. We use chart create to define our logical 2D Cartesian grid topology. When tuning this algorithm, your choice of block size is critical, as it directly alter your communication to computation performance ratio. So it will affect a lot. So you have to be careful on that. Yeah. Okay. So next, another case study, which is cup flat metric example scenario. So this is a performance table showing processor 2, 4, 8, and 6. Yeah, altogether with speed up, you can see 1.8, 3.0, 4.7 here, and 6.4, including the serial fraction. All right, as we learned before, 0.09, 0.08, 0.1, and 0.12. Okay, let's evaluate a real world scenario by applying a curve flat metric to actual performance data. Look closely at the data column on this slide. All right. So on two processor, running on two processor, we achieve a speed up of 1.82, which correspond to an experimentally determined serial fraction of E, which is 0.09. So next, if we use we use a 4 processor, our speed up climbs to 3.08, and our serial fraction drop slightly to 0.08. But when we scale further to 8 and 16, all right, our speed up gains begin to flatten, out at 4.71 and 6.4. All right, this one, causing our calculated serial fraction E to rise, to 0.1 and then 0.12. Okay, how do we interpret all these results actually? Okay, the initial low value, the low value of E tell us that our core algorithm was parallelized very well. However, the noticeable increase in E, as we scale out to 16 processor provides a definite diagnosis. Our system is experiencing growing parallel overhead, likely caused by network communication delay or contention for shared resources. These data tell us that under the current configuration, our optimal processor count tops around 8 to 16 cores. Okay, all right. That's the optimal processor between 8 to 16. All right. Okay. This one regarding profile communication pattern, reduce message frequency, evaluate load balancing. So this is a diagnosis checklist. All right. First, we must profile our communication pattern to keep record. Profile means you keep record pattern to find out exactly where our network latency is stalling execution. Second, we should look into reducing our message frequency, which we can accomplish by aggregating small variable into fewer and also larger data packets. Third, we must carefully evaluate our load balancing to ensure our processor are not wasting time stalled at a barrier. That's very important. Yeah. And then for the ghost cell communication pattern. Okay, so in the diagram shows actually the conceptual overview of a halo region surrounding a local domain. Okay, what's a halo region? Okay, halo region is quite famous in the image processing. Okay, in order to generate the data calculation of the images close by that, okay, so we have a halo region. You need to understand how, because they are using the mathematical to representing like the fire, the image of the fire, image of the surround that, okay, halo, okay, in edges can halo, okay. So in order to represent that, okay, so this is called the halo, okay, halo region, okay, to make it some there is in image processing is quite popular, halo region, because sometimes to increase the the visibility of the image also we need halo, so depends on the problem. Yeah, okay, let's analyze the ghost cell communication pattern, which is industrial standard design pattern for the grid-based domain decomposition actually. Yeah, so the concept, yeah, on creating an artificial halo region around each local processor data domain. This halo region actually contains duplicated boundary data belonging to adjacent neighboring processor. And to ensure correctness, this ghost cell layer must be synchronized and updated before each consecutive computation step begins. The physical thickness of your ghost cell layer is directly determined by your algorithm mathematical stencil radius. Okay? All right. To optimize this exchange pattern, you should utilize non-blocking MPI calls to completely overlay, yeah, boundary communication with inner grid computation. Okay, you should also fine-tune your ghost layer thickness and choose partial decomposition strategies that minimize the overall surface area to volume communication ratio. Okay, all right. So the technique actually, okay, the halo region in the image processing, now they're using in this network. Okay, try to imagine that. Okay, they try to get to the adjacent value of each of the image. All right, so this is the concept implement in another area. Okay, image processing now implement in the optimization, especially in the topic that we discuss right now. All right, okay. Next, very important things. What we get from the our discussion just now. Okay, so this is summary point. Yeah, covering performance metric, parallel pattern, bottlenecks, architectures, and combined models. Okay, in conclusion, let's summarize the core principle required to master parallel software engineering. Yeah, first, always utilize performance metric and scaling laws to analyze your execution data. Second, map your problem onto established parallel pattern like pipeline reduction or divide and conquer to ensure clean design. Third, learn to actively identify and eliminate the primary sources of performance loss, load imbalance, communication overhead, and bad cache management. Fourth, optimize. Yeah, optimize very important. So optimize what? Optimize your code specifically for the target hardware architecture you are deploying on. Next, finally, also combine. You have to combine. Okay, combine share memory OpenMP with distributed message passing, which is MPI, into a unified hybrid model to fully unlock large-scale, high-performance computing cluster. Okay, for the future direction, direction. So look forward. The parallel programming landscape continue to evolve rapidly across four major issue right now. Heterogeneous architecture, so which require mapping workload across CPU and also GPU system. And next, energy aware parallel computing, which prioritize optimizing our code for power efficiency and performance per watt inside massive data center itself. And also the next, AI-driven auto parallelization, where intelligent compilers analyze sequential source code and introduce parallel structure automatically. And next, advanced performance modeling, which allow developer to simulate and predict code scalability on next generation supercomputing hardware before it is even built. All right. So next one, referencing. So here are the list of standard specification and reference textbook. For further study, I highly encourage you to explore the reference material. You can access official OpenMP specification at openmp.org and the MPI standard documentation at mpiforum.org. And for the textbook reading, please consult using OpenMP by Chapman, Parallel Programming with MPI by Pakiko, and High Performance Parallelism Perl series for advanced case study. All right. Okay, thank you all very much for your time and attention. Hope to see you again. Thank you for listening and bye-bye.